Welcome to the Compiler Design course. In the previous session, we discussed the introduction to code optimization for the compiler. Today, we are going to discuss the code optimization techniques in details. The code optimization is a program transformation techniques which try to improve the code by reducing the space consumed and increase the speed of the compilation. We already see that some type of the code optimizations, that is a machine dependent and a machine independent code. The source code and intermediate code optimization comes under the category code independent code optimization, and the target code comes under the machine dependent code optimization. We are mainly focused on the machine independent, that is in that we are mainly focused on the intermediate code generation phase. In the we only focused on mainly focused on the intermediate code optimization. The source code optimization is done by the programmer, so for the programmer convenient it can be done. We are using some techniques to optimize the intermediate code. We will see it. The code optimization techniques are some of the code optimization techniques are the constant folding, copy propagation, strength reduction, dead code elimination, common sub-expression elimination, and looped optimization techniques. These are generally used in some of them are used as global, and some of them are used in local. It may be applied in the iterative manner, that is after applying constant folding, then we can apply strength reduction, then again we can apply any of these optimization techniques to get the better performance. We will see some of the example in the upcoming sessions. Today we are going to see some basics of these code optimization techniques. Then these are the techniques used to perform the code optimization. Then we come to the first optimization technique, that is constant folding. The constant folding is the process of recognizing and evaluating constant expression at compile time rather than computing them at runtime. We can compute or we can perform some computation rather than in compile time, rather than the running time. We can compute it in compilation time. We can perform the evaluation of the expression at the compile time rather than performing it in runtime. So if all the expressions if contain some of the constant value, if the constant value can be calculated or evaluated at a compile time, then we can achieve or we can achieve better performance in the compilation time. Or we can say that the runtime of the environment or runtime of the program will be reduced by some amount of time. That is, expression with the constant operands can be evaluated at compile time, thus improving the runtime performance and reduce the code size by avoiding evaluating at compile time. That is the process. So here in this expression you can see that here s equal to 4 into 3 plus p. Here s and p are some variables, and 4 into 3 is a 4 and 3 are constant values. So we can evaluate the constant expression, that is 4 into 3 at the compile time rather than it is performed in runtime. So we can improve the runtime performance and also reduce the size of the code. There is no reference. If we directly compute it at runtime, there are 4 reference for, that is S4, 3 and P. But in the case we can eliminate one of the reference also. Then after evaluating the particular expression at a compile time, the code will become S equal to that result, that is 12 plus P. This is called constant folding. We are performing the some operation constant expression evaluation at compile time rather than at runtime. Okay, constant folding may apply to more than just numbers. We can also concatenate the two strings to form the large strings. So the strings are already defined, so we can replace with a combined result in that case also. So here you can see the second expression, that is y equal to 5 plus z star 2. That is according to our rule, we are giving more priority to the multiplication rather than addition. So we have to perform z into 2 first, then that result is added with the 5. So we can't perform in the multiplication or the addition operation because there is the operands in the expression is not constant. If we consider the operator star, one of the operand the z is variable, and we consider plus, here also one of the variable is z, that is variable. So we can perform the constant folding in that situation. If z is a constant, then we can perform. If z is a instead of z, if there is a constant value, then we can perform the constant folding operation. We can also apply the constant folding to strings also. That is for the concatenation of strings and constant strings. The constant strings we can perform the constant folding. Consider the two strings, that is ABC and DEF. We can concatenate it into large strings by constant folding operation. Plus means the concatenation, so we will get the result. So the concatenation of these strings at a runtime can be replaced by or it can be done at the compile time. So the runtime can be reduced. There is a situation of the constant folding. The programmers generally do not write the 4 into 3 directly, but these expressions are relatively common after macro expansion and other optimization such as constant propagation. We will see the constant propagation in the next we will see it in next slide. What is the constant propagation optimization technique? But the programmer generally do not write the such as 4 into 3, but the expressions are relatively common after the macro expansion. You see the macro expansion in the overview of the compiler. After the macro expansion, there is a chance that the expression will become all constant values, or some part of the expression will become the all constant values. Or sometimes other optimization, after other optimization also we will get some constant values in the expression. So this is about the constant propagation, constant folding. Then next we will see the constant propagation. We can say that the copy propagation techniques is a process of substituting the values of non-constants or variables in the expression at compile time. So we are substituting the values of constants and variables in the expression at compile time to perform the substitution at the runtime, rather than substituting the values of the variables and constant at a runtime. We are substituting the values of constant and variables at the compile time in the expression. So there are two classification for the copy propagation. There is constant propagation and the variable propagation. The propagation means we are substituting the values. So the constant propagation is the process of substituting the values of the non-constant in the expression at a compile time. That means if we consider the expression that is first part, that is constant propagation, here the x equal to 3 then is the first statement, and y equal to x plus 4 is another statement. The value of the x can be substituted at the usage of x. The value of x can be propagated to the use of the x. That is, the x equal to 3 can be propagated or substituted at the usage of x. So after constant propagation, that is propagation means copying or substituting, the value of x, the value of x is constant, that at the place of usage of x, the particular code will become x equal to 3. That is a general in the previous also the x equal to 3. Then y equal to x plus 4 become y equal to 3. That is the value of x plus 3 plus 4. That is the situation. This is the constant propagation. We are substituting the constant value at the usage of that particular variable. So after the constant propagation, the value will become the x equal to 3 and y equal to 3 plus 4. Here we can apply the constant only. In the case of y, all the variables in the expression 3 plus 4 is constant. So we can perform the this evaluation of the expression at a compile time. So after constant folding, the value will become x equal to 3 and y equal to 7. Y equal to 7. That is the case of constant propagation. Then I'll come to the variable propagation. The variable propagation also is the process of substituting the values of variables in the expression at a compile time. So we are substituting the values of the variables in the case of variable propagation. Consider a situation x equal to y, then x equal to z equal to x plus 2. So x have a variable x is assigned by a variable y. That value is used by x. So that value is again that x value is used again in the second statement. That is z equal to x plus 2. So the value of x can be substituted at the place of y. The value of x is y, that can be replaced by the usage of x. So after the variable propagation, it will become x equal to y and z equal to y plus 2. Then it is mainly used to perform some other optimization techniques like the red code elimination. Here, if we are not using the x in the upcoming statements, then we can eliminate x equal to y statement as dead code. There is no usage of the variable x, so we can eliminate that particular statement x equal to y from the program. That is the idea of the variable propagation. That is about the variable propagation and constant propagation. That these two optimizations comes under the category copy propagation. Then next code optimization technique is strength reduction. Strength reduction is a compiler optimization. That is, it is going to perform some compilation where compile optimization where expensive operations are replaced with equivalent but less expensive operations. That is the idea of strength reduction. We are replacing a expensive operation by a less expensive operation that is equivalent to the expensive operation. That is the idea of the strength reduction. As we all know, the multiplication will take more amount of time than addition. So compared to addition, multiplication is a expensive operation. So we can replace the multiplication operation by addition. That is on a strength reduction method. Here is in our example, x equal to 2 into 2 multiplied by y. That is 2 into y. So that can be replaced by some addition operator. That is x equal to y plus y. That will give the same result as x equal to 2 into y. But here the expensive operation is replaced with a inexpensive operation or less expensive operation, that is addition. That is one of the example. Then the same example is taken the second option also, that is x equal to 2 into y. Here also we can replace the multiplication by shifting that number by one place. In order to perform the multiplication by 2, we can perform the left shift operation. That will give the same answer. If you consider one number, that is binary number, that is 101, that is 5, then we are going to multiply it by 2, that is 10, then we will get the result as 1010. So instead in addition to perform the multiplication, we can shift that value by one place. So 101 is shifted to left one place, then we will append 0 at the end of the particular code. So it will become 1010. Without addition, by using only shift operation, we can perform the multiplication by 2. That is the situation. So if you want to perform multiplication by 4, we only need to shift that code to left by 2 positions. That is the idea. So the multiplication operation can be replaced with the shift operation, that is left shift operation. So it is another strength reduction category. The another example is to p equal to q divided by 4. In order to perform the division, we can eliminate that or replace the division operation by right shift. We want to divide the number, that is 1000, that is 8, by 4. Then we have to perform two right shift operation to get the answer. If you want to perform division by 16, we have to perform the 4 right shift operation. That is the idea. Here we are in our example, p equal to q by 4. So we have to perform the division operation by 4. In addition to that, we can perform some right shift operation by 2. So that is shown in the result, that is p equal to q, right shift 2 positions. That is about the strength reduction. Strength reduction means we are replacing an inexpensive or less expensive operation in addition to an expensive operation. Okay. Then the next technique is the code elimination, dead code elimination. Dead code is a section in the source code of the program which is executed but whose result is never used in anywhere or any part of the computation. Or we can say that that code which can never be executed at the runtime. We are going with that is or we can say that it is a unreachable code. In some situation, some part of the code of the program does not affect the program execution, or we can say that it is unreachable. Some code is never reachable from the program. Some part will not execute in any situation, that is in any conditions it will not execute. That is a situation of the dead code. So we can eliminate the dead code by using some analysis. The dead code elimination is an optimization that remove the code which does not affect the program result. Removing the result or removing the dead code have several benefits. That is, it shrinks the size of the program. Also, it allow the running program to avoid executing irrelevant operations. We can eliminate it. Then come to the one example, that is x equal to 2. Then next statement is a conditional jump statement, that is if x equal to 2, then we will print s6, else we will print it. That means if the condition is satisfied, then we will print only one statement s6. Then if that condition is not satisfied, then we will print it. From this code you can say that the condition x greater than 2 will always false. That is, before the statement the value of x is 2, so it will not return a true as the result. So always the expression will evaluate the false, and it will not go to the print statement, print s6. So it will always perform the else part of the code. So the code if x equal to 2 and print s6 is the dead code. If we remove that code, also we will remove the else part also. So it will become the code will become x equal to 2, then print it. That is situation. That is, if based on our logic, if the value of the x is not greater than 2, we are going to perform the print it part. So here we are fixing the value of x equal to 2, so it will never print the s6. So we can eliminate the such of codes by writing the code as x equal to 2 and printf it. So after that code elimination, we will get the result as the x equal to 2 and printf it. So we in this situation we reduce the size. So the dead code elimination shrinks the program size, and it allows running program to avoid executing irrelevant operations. The irrelevant operation here are x greater than 2 and print s6, that is comparison and some a set of x, which reduce its running time. It can also enable further optimization by simply finding the program structure. That is the case of the dead code elimination. Then we are applying these code optimization takes one after another, then we will get a better code. The next code optimization techniques is common sub-expression elimination. In sometimes same expressions maybe appear in more than one place, and that performance can be improved by generating the code for that expression in one place. That is a situation of the common expression elimination. That is, the same expression appear in more than one place, and that performance can be improved by generating the code for that expression in one place. An expression is the common sub-expression elimination if the expression was previously computed and the value of the operand have not changed since the previous computation. Then we can say that it is a common sub-expression. Here take an example, that is a equal to b star c plus g and d equal to b star c star e. In these two statements, you can see that the same expression is calculated or evaluated twice. That is a equal to b star c, then plus g. In the second statement, d equal to b star c star e. In these two statements, we are computing b star c twice. That is, in the first statement also we are computing the b star c. In the second statement, we are also performing or evaluating the b star c. The recomputing the expression can be eliminated by using the values of the previous computation. So we can perform only once the expression, that is B star C once, and we can use it in the upcoming statements. That is the idea of the common sub-expression. Here B star C is the common sub-expression, so the computation of this common sub-expression can be computed only once. We can eliminate the recomputing of the expression. That is the idea of common sub-expression elimination. So we will perform the B star C, that is common. We first identify the common sub-expression, then we will evaluate that common sub-expression only once, and that value is used in the upcoming statements. So B star C is evaluated once and it is stored in the location temp, then that temp is used in the so A equal to temp plus G, then D equal to temp star G. That is the idea of common sub-expression elimination. Then this common sub-expression elimination can be found or used to can be identified by using DAG. So that is one of the use of the DAG. That is, DAG can be used to eliminate common sub-expression. So consider a particular statement, that is x equal to a plus b plus a plus b plus c. Here from the viewing the particular statement, we can identify that a plus b is the common sub-expression, but it can be identified by using some DAG. We already see that the DAG is the optimized one of the syntax tree. Then we will eliminate the recomputation in the case of DAG. So the expression, that is a plus b, is evaluated first, then the a plus b plus a plus b is evaluated, then that result is added to C to get the final result as x. So a plus b will evaluated, then that is used again to compute the a plus b plus a plus b. So that is happening in the left side of the DAG. Then that value is again used to perform the addition between the a plus b plus a plus b plus c. That is about the DAG. You can see the DAG here. Then it can be used to eliminate the common sub-expression. Here, if we generate 3-address code from the DAG, you can assign some temporary variables to each and every non-terminal. That is, non-terminal means operator node. So first you will assign T1 to one of the particular non-terminal, then T2 to another non-terminal, T3 to other non-terminal. We will get the 3-address code. This is how the 3-address code is generated or from the DAG. The T1 equal to then a plus b, then T2 will become, that is T1 is used to is the left operand of the addition. So T2 equal to T1 plus T2, sorry, T2 equal to T1 plus T1, then T3 will become T3 equal to T2 plus C. That is about the common sub-expression elimination. This is how the 3-address code is evaluated or generated from the by using the DAG. Or the common sub-expression can be eliminated. Here the common sub-expression is eliminated by using the DAG. That is the applications of DAG. Then we can see some different loop optimization techniques in the next session. Okay, thank you.